All right, let's talk about the mixing of ideal gases, which is going to help us really set the stage for mixing of solutions. But for now, ideal gases, this is going to help us kind of start to think about the thermodynamics of mixing. So in the beginning of our phase equilibria discussion, we developed an equation which went as the following. Mu equals mu standard plus RT natural log of P over P standard. So we developed this in phase equilibria to think about how the chemical potential of a material changes with respect to changes in pressure. So now as we apply this to a mixture, what we want to think of is this mu standard is for our pure material, and then now these parameters, mu, and this pressure up here is going to describe our mixture, okay? So if we're thinking about our G initial state, okay, that's going to go something like Na mu A plus Nb mu B. And then our final state we can also describe in a similar way. We just have to use these chemical potentials in a different way. So let's do that. So G initial is going to equal the following. So I'm going to say Na, and now I'm going to plug in the chemical potential for mu A in the mixture. So that says mixture, but really we should note that that's for the species in the mixture. This is just the pure material not in the mixture. So now that's going to go as the following. So mu A standard plus RT natural log, and then that will be the pressure of A over some standard reference pressure. And in this case, our standard reference pressure is always going to be 1 bar, which will allow the units of this to cancel in the natural log. And then now that's going to be plus number of moles of B, and then we can write the same thing. Chemical potential standard of B, RT, natural log of P over P naught. So now when we mix these things, we'll have an individual partial pressure of A and an individual partial pressure of B, which will give us our total pressure, right, through Dalton's law of partial pressures. By the way, we could have recorded a whole video on doing partial pressure as a partial molar quantity, and it would have worked out the same thing as partial molar volume. So now when we go to say G final, this is going to be the following. So now they've mixed, and this is going to look really subtle, but it's important to note these differences. So I drew a line here just to really signify that now I'm doing a new line of work here. So now that's going to be Na times now specifically mu A standard, and there's a really subtle change here, but that's now going to become RT, and it's now the partial pressure of A over some standard pressure, and now that's NB times its expression plus RT, and now that's the partial pressure of B. So again, I know that's like really, really subtle, and it doesn't look like much changed, but it's important what's going to happen. So now we can say the delta G, the change upon mixing, is going to be G final minus G initial. And when we go through all of that, we're going to end up with the following. So I'll write all of that out. So let's see. So that's going to end up being Na RT natural log of PA over P plus NB RT natural log of PB over P. So we might be thinking, where did all of those standard chemical potentials go? Well, when we did final minus initial, right, mu A subtracts from mu A and mu B subtracts from mu B. So the only thing that we have left are those quantities Na times RT and those partial pressures, okay? So if we divide this whole thing by the total number of moles, N, and remembering that for ideal gases, mole fraction could be Na over N total, which is the same thing as saying Pa over P total. So that's where I was confusing myself. That needs to be total, right? So then we can rewrite and say delta G of mixing is nRT. So my N is now the total number of moles, N. Let's see, times chi A, natural log of chi A, plus chi B, natural log of chi B. And what I want to note here, for any value of chi, this will always be less than or equal to 0, right? So mole fractions are any number between 0 and 1. So if the mole fraction is 1, corresponding to a pure material, the natural log of 1 is 0, right? So we can see that in this graph right here, where if we've got pure material, we haven't done any mixtures yet, so there is no delta G of mixing. But if chi A is some value between 0 and 1, that's always going to be a negative, and thus we can see it is always spontaneous to mix ideal gases. And specifically, we get the maximum spontaneity when our mixture is 50-50. Okay, so that's pretty cool. So we could also then, in this same discussion, think about what happens to the entropy on mixing ideal gases. So right here on the side, I can write the partial of G with respect to changes in T at constant pressure and constant number of moles equals negative entropy, right? So very easily, I can just write the change in entropy upon mixing by putting a negative sign and taking this expression, the derivative with respect to temperature. So that just becomes negative nR times chi A, natural log of chi A, plus chi B, natural log of chi B. And as we might guess, that expression will always be greater than or equal to 0 for the same arguments because we have a negative sign there. And furthermore, so I didn't do very good board management here. If we remember our definition, another definition for delta G equals delta H of mix minus T delta S of mixing. Well, because that always has to be negative, right, we can conclude that delta H of mixing ideal gases must always be 0. So delta G of mix is always negative, delta S of mix is always positive, and delta H of mixing ideal gases is always 0. Which all makes good sense when we think about the previous discussions we've had, that in ideal gases there are no interactions. So why would there be any enthalpy release or absorption upon mixing those things? And of course, it should be always spontaneous to mix ideal gases. So that's what we can conclude from these equations. Okay, we will move on now into talking about what makes an ideal solution, and we're going to use this whole idea on ideal gas mixtures to help us with that discussion. All right, I'll see you then.